Dear students, myself Dr. Mallikarjun S. Biradar, Assistant Professor in Mathematics, Government First Grade College, Basava Kalyan. The 31st session of Graph Theory 2, that is Introduction about Colorability. Already we have completed 2 units. The second unit was planar graphs. Now the third unit is colorability. Today we are going to discuss about the introduction to colorability. Already in the previous unit we have studied planar graphs. So now in this chapter we will see the application part of the colorability. The planar graphs. So we will see how the planar graphs are useful in this topic called colorability. Okay. Now let me introduce or give some introduction about the colorability. Color, when we get the word color, we used to get different colors in our mind. I think you might have seen the maps, maybe the Indian map or any state map, even you might have seen the world map. There, the different countries are colored with different colors. Why? It is because we need to identify the countries. If we color all the countries with the same color, we cannot identify. For that reason, the countries are colored with different colors. For example, if I consider the African continent, as you know, there are 53 countries in the African continent. So if we color each country by a single color, we require 53 different colors. Now the question is, how many colors we need to use to color such a map? It may be African continent or it may be world map. Okay, so that important concept we are going to discuss in this topic. Okay, so now when we color the map of a country, what we used to see? We used to see that the states with a common boundary are colored with different colors. Okay, let me consider here, because the reason is that, as I have told right now, it is for easy identification of the states, or you can say countries. If you consider a map of a state, districts. If you consider a map of a country, states. If you consider a map of the world, so we need to identify the countries. So for that reason, for easy identification, we color with different colors. And moreover, the countries with a common boundary, it implies those who are having common boundary between two countries. For example, India and Pakistan, India and China, India and Bangladesh. So there is a boundary. Like that in the world, there are countries with a common boundaries. So such a common boundary countries, we must color with different colors. Otherwise, we cannot identify very easily. So for that reason, when we color the map of a country, we see that the states with a common boundary, you can say common boundary or you can say adjacent states. In terms of states, if I use adjacent states, you can use, or you can use common boundary, are colored with different colors for easy identification of the states. Okay, as I have told right now, if we consider the African continent, there are 53 countries. Okay, so we need to color the map of this continent in such a way that the countries with common boundary, or you can say adjacent countries, are colored with different colors. So how many colors we require? Whether 53 colors? That is a question, isn't it? One used to get such question in the mind. Okay, so this topic deals with the colorability. That is the importance of the planar graph which you are going to use in this topic, that we will see in detail. Okay, so right now, what you mean by a coloring problem is a question. What is the coloring problem? So one might ask, what is the minimum number of colors required to color the map so that adjacent countries receive different colors? This is called the coloring problem. Okay, simply if you, without thinking, if you use a single color, different colors for different countries. For example, African continent, if you consider, if you use 53 different colors, of course you can color, but that is not a task. The task is that we want to minimize the number of colors, so that within the minimum number of colors we need to color the map of such a continent or even the world map. So what is the coloring problem? One might ask, what is the minimum number of colors required to color the map so that the adjacent countries, or you can say the countries with a common boundary, receive different colors? So this is called a coloring problem. So we want to minimize the number of colors. Okay, that is the coloring problem. So we want to color the map, but we want to minimize the colors also. So clearly a map, if you see any map, what is that map? A map is a plane graph, isn't it? Very simple. If you consider the map of even Indian map, what you will see? It is a plane graph. See, in the planar graphs, what we have studied, planar graph, if it is embedded in the plane, it is called a plane graph. So in the plane graph, we used to see the faces, isn't it? Interior faces and one exterior face will be there, isn't it? So those faces are considered as the countries or the states, isn't it? So clearly a map is a plane with the states corresponding to faces. Okay, we should be able to color the faces of a plane graph in such a way that the adjacent faces, and what do you mean by adjacent faces? That is faces sharing a common line, receive different colors. Okay, that is the idea of coloring a map. Okay, so what we come to know, our aim is to minimize the number of colors. And what is the map? Map is nothing but it is a plane graph. So the plane graph, which is a planar graph, of course, embedded in the plane, is called a plane graph. Okay, so this is how, as I said earlier, the concept of planar graphs and the plane graph and the faces, we are using all those ideas in this topic. Let G be a plane graph. As you know already, planar graph, if it is embedded in the plane, it is called a plane graph. And G star be its dual. Already we know how to construct the dual of a plane graph. It is a planar graph and embedded in the plane, and we consider all faces as vertices, including the exterior face, and two faces are adjacent, that is the vertices corresponding to two faces are adjacent if those two faces have a common line or edge in between. Okay, so that already we have discussed in detail. So you know already the clear picture about the geometrical dual. The face coloring of G, see the plane graph, after getting the plane graph, what you are doing, you are finding its dual. So in a dual, the vertices represents the faces. It implies our aim is to color the faces. So coloring the faces is nothing but coloring the vertices of a dual graph. See, that is the beauty of a graph theory, how it is applicable. So let G be a plane graph and G star be its dual. The face coloring of G is equivalent to the vertex coloring of G star. So the previous topic, planar graphs and its geometrical dual, are very useful in this topic. Okay, as I said earlier. So in general, a graph G with P vertices can be colored in such a way that no two adjacent vertices receive the same color. So instead of saying the coloring the map, what we are saying now, we are saying a graph, because it is a plane graph and we are finding its geometrical dual. So now it is a graph. So in general, a graph with P vertices can be colored in such a way that no two adjacent vertices have the same color. So now the question is, what is the minimum number of colors to require the coloring of the vertices? So this is a coloring problem. So that was the coloring the map. So now it is called the coloring problem. Okay, so what is the coloring problem? Minimizing the number of colors to color the adjacent vertices. No, not only adjacent vertices, coloring the vertices in such a way that no two adjacent vertices have the same color. So it implies the adjacent vertices must be colored with different colors. Okay. So in this unit we study the colorings of graphs. So in this topic we are going to study how to color the graphs or coloring of graphs, and we discuss the vertex chromatic number. See, one concept we are getting here, chromatic number. See, I am using the word, we want to minimize the number of colors. Okay, so minimizing the number of colors. So there we get a concept of chromatic number that we are going to discuss in detail. So just it is an introductory talk or introductory session. So I am using the word. So we discuss the vertex chromatic number. Okay, a graph G with P vertices can be properly colored in many different ways. What do you mean by properly colored? No two adjacent vertices have the same color. It implies the adjacent vertices must be colored with different colors. It is called properly coloring or properly colored in many different ways using a sufficiently large number of colors. So this property of a graph is expressed by means of a polynomial, and we study the chromatic polynomial which was introduced by Birkhoff in 1912. Okay, so Birkhoff, he was a mathematician, or you can say the graph theorist. So he got this concept chromatic polynomial in the year 1912. Also we study the four color problem that is called 4CP, four color problem. An important thing is that we are going to discuss one important what we can say conjecture. Why it is called a conjecture, why it is not a theorem, that we will discuss in detail. So another important thing is that four color conjecture. In short, it is called 4CC. And at the end we express the conclusion of 4CC. So what is four color problem? What is the four color conjecture? Why it is called a conjecture rather than a theorem? That we are all discussing in detail about this coloring, or you can say the colorability. So in brief, I have given introduction about the colorability in the first session. Okay, so what we have discussed so far. So I have given the introduction about the colorability, what is the coloring problem, and what is the importance of a map, how it is converted in terms of a graph, and what is the coloring problem actually. So minimizing the number of colors to color a graph in such a way that the adjacent vertices must have different colors, or you can say no two vertices with a common boundary, or you can say with adjacent vertices must have different colors. Okay, so with this we conclude today's session. So we will see in detail in the coming classes. So these are the references already I have mentioned in the previous class also. Graph theory by Frank Harari, graph theory by Professor V.R. Kuldi, or even if you want you can refer a first course in graph theory by S.A. Chodama. Okay, so these are the reference books. So if you want you can refer. So with this we conclude today's session. Thank you.